Hello friends, welcome to my lecture series on digital signal processing. In the previous lecture, we saw the concept of Fourier transform and Fourier transform of some standard functions. In this lecture, we shall address the properties of Fourier transform, and I believe if you master the properties of Fourier transform, one can solve many complex problems in signal processing and communication system. What is the properties of Fourier transform, or what is the significance of properties of Fourier transform? As mentioned, if x of t is transformable to x of omega, then if you make any changes in x of t, what is the impact on Fourier transform? And that is given by properties of Fourier transform. Consider the first property, duality. It is a very important property using which one can solve spectrum of many complex functions without solving the first definition, which is the integral equation of Fourier transform. Now here, the duality property is if x of t is transformable to x of omega, then capital X of t is transformable to 2 pi small x of minus omega. The meaning of this equation is, suppose if you have an equation in frequency domain, that is x of omega, and if you come across a time domain function where omega is replaced by t, then how one can find the spectrum of such a signal? And that can be easily found using property of duality. First, we'll see the proof of this property, and then we'll see the example. So consider Fourier inverse transform, where x of t is equal to 1 over 2 pi integration of x of omega e raised to j omega t d omega. Here we have replaced t by tau as a dummy variable for the proof. Now if you substitute omega equal to t, then above equation can be simplified to 2 pi x of tau is equal to integral of x of t into e raised to jt tau dt. And now when tau is equal to minus omega, the above equation will become integration of x of t into e raised to minus j omega t dt is equal to 2 pi small x of minus omega. The left hand side equation is nothing but the Fourier transform, while the right hand side is frequency domain representation of capital X of t. This is a proof for the duality. Now we'll use this property to compute Fourier transform of a sinc function in time domain. Now sinc function in time domain is defined as sinc of t is equal to sine of pi t divided by pi t, which we already defined in our previous lecture. And if you are not aware, you can refer the lecture on Fourier transform. Now this function will become 0 for t is equal to plus minus 1, plus minus 2, plus minus 3, and so on. Now we already know that the spectrum of rectangular pulse is sinc function, where rectangular pulse is in time domain while sinc function is defined in frequency domain. Now here we can make use of duality property, using which we can find out spectrum of sinc function in time domain. So we have to exchange the variables here. By applying duality, omega will get replaced by t, and hence you will get equation a tau sinc of t tau upon 2 pi transformable to 2 pi pulse function with respect to minus omega. Now here we are interested in sinc of t, and therefore we have to substitute tau upon 2 pi is equal to 1. After manipulating the terms on both sides and substituting tau by 2 pi is equal to 1, you will get a equation sinc of t is transformable to, you will get equation 1 by a pulse function of omega with parameter 2 pi, that is a width of pulse function in frequency domain. So here it shows that sinc function is transformable to a low pass filter with a cutoff frequency pi. Now solving frequency spectrum of sinc function is very difficult using first definition of Fourier transform integration. However, it can be easily computed using duality property. Now consider another function which is a DC function having magnitude 1, and it is transformable to 2 pi delta omega, which is quite intuitive because DC function has a frequency 0. So one can equivalently say that the Fourier transform of a DC function is nothing but a sine wave with a frequency which is represented as an impulse function in frequency domain at omega equal to 0, and hence 1 is transformable to 2 pi delta omega, where 2 pi is a simply scaling constant. Now we can prove this using duality property. So here x of t is equal to delta t transformable to 1, which we already know, and hence by applying duality property, capital X of t is equal to 2 pi delta of minus omega. However, the impulse function is always a symmetric about y-axis, and hence delta of minus omega will become delta of omega. So in two steps, we can prove the Fourier transform of a DC function is a impulse function. Now consider unit step function, that is x of t is equal to u of t, and that is transformable to pi delta omega plus 1 by j omega. Unit step function can be expressed in terms of a signum function. The computation of Fourier transform of unit step function is very difficult because the limits of integration from 0 to infinity will result in infinite integration and problem cannot be solved. However, unit step function can be equivalently represented in terms of signum function. Now signum function is 1 for t greater than 0 and minus 1 for t less than 0, and if it is shifted in upward direction by 1 unit and divided by 2, you will get unit step function, and hence unit step function can be expressed as half of 1 plus signum t. So now the Fourier transform of unit step function can be computed by computing Fourier transform of 1 and Fourier transform of signum function. We already computed Fourier transform of signum function in our previous lecture of this series, which is 2 by j omega, and hence the Fourier transform of unit step function is given by pi delta omega plus 1 by j omega, where 2 will get cancelled from both the terms. Now consider another important property which is called time shifting property. So whenever a signal is shifted in time domain by some arbitrary amount t naught, then we can see that there is no change in the shape of the signal, and hence the magnitude spectrum of a signal will remain same, only it will experience a phase because the time shift is always related to the phase shift, and this is an important point one should understand, because the phase shift is time shift multiplied by the frequency, and it is expressed as e raised to j theta, and therefore the Fourier transform of x of t minus t naught is x of omega into e raised to minus j omega t naught. If you calculate magnitude, then the magnitude remains same as x of omega, and the magnitude of complex exponential becomes 1. So only phase spectrum gets affected whenever signal is shifted in time domain. The proof of this property is pretty straightforward. Just substitute x of t minus t naught in first definition of the Fourier transform integration. Now here t minus t naught is replaced by tau, and therefore t becomes tau plus t naught and dt equal to d tau. So when this equation is simplified, you'll get Fourier transform of x of t minus t naught is equal to integration of x of tau e raised to minus j omega tau plus t naught into d tau. Now here e raised to minus j omega t naught is constant, and it will come out of the integration, and the right hand side term in the integration becomes Fourier transform, and hence it is proved that Fourier transform of x of t minus t naught is equal to x of omega into e raised to minus j omega t naught. Now another important property of Fourier transform is frequency shifting property, which is also called modulation, and this is a very important property. One can use it in solving many problems in signal processing and communication system, especially analysis of various modulation techniques such as amplitude modulation, frequency modulation, phase modulation, and even digital modulation techniques like ASK, PSK, and FSK. Now here, the frequency shifting property is defined as if x of t is transformable to x of omega, then x of t into e raised to j omega naught t is transformable to x of omega minus omega naught. Now here, this one is a arbitrary function x of t having Fourier transform x of omega, and when it is multiplied with e raised to minus j omega naught t, which is nothing but a sinusoidal function expressed in complex exponent having frequency omega naught, then signal frequency spectrum is shifted in frequency domain, and therefore the new transform becomes x of omega minus omega naught, where x of omega is shifted to omega naught. Now this property can be proved easily using first definition of Fourier integral by substituting x of t as x of t into e raised to j omega naught t. Now here, when the equation is simplified, you'll get a new frequency omega minus omega naught in a Fourier transform equation, and hence the Fourier transform becomes x of omega minus omega naught. Now we'll see one simple application of frequency shifting property of the Fourier transform, which is nothing but design of antenna system in transmitter and receiver. So whenever you want to design an antenna, the antenna length should be lambda by 4 to receive a frequency f. Now lambda by 4 is a minimum length of an antenna required, where lambda is equal to c by f. So in order to design a practical antenna system, antenna length should be as small as possible, and that is possible only when frequency is large. So one can compute a practical antenna length for which what is a corresponding carrier frequency, and that is a design equation. So here we'll consider a simple modulation technique which is called amplitude modulation with double sideband suppressed carrier, and it is defined as m of t into cos of omega c into t, where m of t is a modulation signal. Now here we can use a Euler identity for cos of omega ct, and when it is substituted in the equation of AM modulation signal, we will get two terms, m of t into e raised to j omega ct plus m of t into e raised to minus j omega ct. Here we can apply the modulation property to each term, and we'll get the spectrum of AM modulation double sideband suppressed carrier signal as half into m of omega minus omega c plus m of omega plus omega c. So here you can see there are two sideband spectrum, and hence such type of AM modulation signal is called double sideband, but there is no carrier signal, and hence it is called suppressed carrier. Now we'll see another very important property which is called a scaling property. So here, if x of t is transformable to x of omega, then x of at is transformable to 1 upon modulus of a into x of omega by a. So here the scaling is multiplied in time domain, and therefore it will get divided into frequency domain, which is a quite intuitive, because whenever a signal is compressed in time domain, it changes rapidly, which means it has high frequency component, and hence it expands in frequency domain and vice versa. And therefore scaling parameter multiplied in time domain becomes a division factor in frequency domain. So consider a pulse function with pulse width tau having frequency spectrum sinc function, and whenever it is compressed in time domain, that is if a is greater than 1, then it will get expanded in a frequency domain. The proof is pretty straightforward. So one can find out Fourier transform of x of at by substituting x of t is equal to x of at. Now here we can use a method of substitution where at is substituted as a tau, and therefore t is equal to tau by a, and hence dt is equal to d tau by a, and the limits of integration will remain same. And therefore Fourier transform of x of at is equal to integration of x of tau into e raised to minus j omega by a tau dt by a, which will become 1 upon modulus of a to x of omega by a. Now here the question is, why in this equation 1 by a is replaced by modulus of a? The answer is a can be positive or negative. Now above relation is valid for positive value of a, but even if you substitute negative value of a, then power of exponent term will become positive. The whole integration is multiplied by -1. Now when you convert again back to Fourier transform where tau is replaced by minus t, you will get the same equation with the positive value of a. So what it implies, irrespective of positive or negative value of a, the final equation remains same, and hence a is replaced by modulus of a. So you can prove that by simply substituting a equal to minus a. We shall see the application of scaling property in a wavelet transform. Wavelet transform itself is another subject. So here we'll see the concept of wavelet transform and how scaling property is used in definition of Fourier transform. So wavelet function is defined as psi of t with parameters a and b is equal to psi of t minus b upon a. So here the scaling parameter is used as 1 by a instead of a in order to maintain the mathematical simplicity. In property we saw that when a increases in time domain, signal get compressed. So it is a reverse process, and hence instead of multiplying with a in wavelet function, it is divided by a. So what it says, when a is increased, function in time domain will also get increased, that is expanded. And when a is reduced, the function in time domain will get compressed. In this equation, the parameter b is a simply time shifting of function psi t. So psi t is called mother wavelet. The shifting of the signal is provided by b, while scaling of the signal is provided by a. So basically it provides a short wave which is called wavelet, which can be shifted on time axis to span entire signal, and signal can be observed with a different resolution with the help of a parameter a, and that's why it allows simultaneous time and frequency resolution in a wavelet transform, and it offers huge amount of applications, especially analyzing transient signal. Now we'll look into the wavelet transform. So wavelet transform is again a dot product of x of t, where x of t is projected on psi of t minus b upon a. So it is the same as Fourier transform, where kernel function is psi of t with parameters a and b. However, it offers simultaneous time and frequency resolution, which is not possible in Fourier transform. And this is one of the application of scaling property of Fourier transform. So here consider psi of t is transferable to boldface psi of omega, that is a spectrum of psi of t, or Fourier transform of a psi of t. Then Fourier transform of psi of t minus b upon a is given by modulus of a psi of a omega into e raised to minus j bt. So we applied the first property, which is a scaling property. So since scaling parameter is 1 by a, we'll get modulus of a multiplied with psi of a omega. And then there is a time shifting property applied to the parameter b, which will give the phase shift of bt, and it is expressed as e raised to minus j Bt. Now here one has to understand one important point, that as a tends to 0, the mother wavelet psi of t will get compressed in time domain. And as a tends to 0, it becomes an impulse function. And hence psi of ABT tends to delta t minus b. And if you replace b by n to discretized in order to implement in real life scenario, then the wavelet transform of a time domain function x of t is given as integration of x of t into delta t minus n dt. Now the product of any function with delta t will exist only at the point of impulse function. Now here impulse function exists at t equal to n, and therefore x of t will exist only at t equal to n, which will become constant. It will come out of the integration, and then final integration is nothing but integration of impulse function, which is 1, and hence the wavelet transform becomes x of n. And this is a very important step in understanding wavelet transform, which says that whenever signal is observed using wavelet transform at highest time resolution, that is whenever wavelet function becomes very, very small in time domain, it is equivalent to a sampled version of analog signal. And that is a good starting point in understanding of wavelet function. We'll have one more lecture on wavelet transform in our subsequent lecture. Now consider a derivative in time domain, which is a very important property of a Fourier transform. And it says the Fourier transform of first order derivative of x of t is transformable to j omega into x of omega. This property can be proved by substituting x of t is equal to derivative of x of t. Now here this problem can be solved by applying integration by parts, which is defined as integration of u into v dt is equal to u into integration of v minus integration of the derivative of u and previous integration of v. So in general, one can write u into v formula of an integration where u is a derivative term while v is an integral term, and it can be extended up to infinity. So this is a generic rule of integration by parts. Now when we apply to above equation, you'll get Fourier transform of derivative of x of t is equal to e raised to minus j omega t into x of t with limits of integration from minus infinity to plus infinity. Here we are using derivative term as v, while e raised to minus j omega t as a u. And therefore in the first term, you'll get e raised to minus j omega t into x of t with limits of integration from minus infinity to plus infinity, and it will become 0 because e raised to minus infinity is 0 and x of minus infinity is also 0, and hence effectively this term becomes 0, and you'll get a final expression as integration of e raised to minus j omega t x of t dt multiplied by j omega. So the integration is nothing but the Fourier transform of x of t, and hence one can prove that Fourier transform of a derivative is equal to j omega into x of omega. Now what is the physical interpretation of this equation, j of omega into x of omega? So here if we'll take a modulus, then the modulus of j omega term is omega only multiplied by x of omega. So what it implies, as frequency increases, Fourier transform of overall term, that is a differentiator, also increases, and hence it acts as a high pass filter, and it can be implemented using simple RC filter followed by an operational amplifier. So operational amplifier here, it avoids a loading effect and it provides an ideal differentiator circuit. This is a very popular circuit which is called high pass filter. So differentiator operator can be implemented as a high pass filter using RC network. Similarly, we can see the low pass filter, and the property is called integration in time domain. The Fourier transform of integration of x of t is given by x of omega by j omega plus pi x of 0 delta omega, and it can be proved very easily using Fourier inverse transform formulation, and you can take it as a homework problem. Now the low pass filter can be implemented using RC network where the position of R and C are reverse, followed by an operational amplifier which avoids the loading effect. So here integrator and differentiator forms system in many signal processing applications. Now we'll see another important property, convolution in time domain, which is basically called a filtering operation in time domain, and that is defined as x of t convolved with h of t, where star notation indicates a convolution operation, and mathematically it is defined as integration of h of tau into x of t minus tau d tau, where tau is a dummy variable. Now here, if x of t is transformable to x of omega, y of t is transformable to y of omega, and h of t is transferable to h of omega, where h of t is called impulse response of a linear time invariant system. X of t forms input to the linear time invariant system, and y of t forms the output of LTI system h of t. Then y of omega is equal to h of omega into x of omega. So the convolution property of the Fourier transform is nothing but Fourier transform of convolution of x of t with h of t is equal to multiplication in frequency domain, that is h of omega into x of omega. It can be proved very easily using first definition of Fourier transform integral. So here we can substitute x of t is equal to x of t convolved with h of t in Fourier integral, as shown by the blue color equation. And whenever it is simplified by changing order of integration, because two integrations, one is with respect to tau and second one is with respect to t, are independent, and hence the order of operation can be changed. In previous integration, we are integrating with respect to t first and then with respect to tau. So now we can integrate with respect to tau first and then with respect to t. So here, when integration with respect to t is performed on two terms, x of t minus tau into e raised to minus j omega t dt, by applying time shifting property, you'll get a Fourier transform x of omega e raised to minus j omega tau. And then solving this integration by taking x of omega outside the integration, because it is constant, you'll get final equation as a Fourier transform of h of t or h of tau. And hence the Fourier transform of convolution in time domain of two functions is equal to product of these two functions in frequency domain. So this is a very important property of a Fourier transform, and it is called a filtering operation in time domain, and it will be very useful in the analysis of discrete time systems, where we shall see the analysis of FIR and IR filters. Now similarly, one can have a convolution in frequency domain as well, where the convolution in frequency domain conceptually is same as convolution in time domain mathematically. So convolution in frequency domain of x of omega with h of omega is equal to integration of h of tau x of omega minus tau d tau. So here tau is a dummy variable. So it implies whenever you convolve in frequency domain, you'll get a product in a time domain. So Fourier transform of multiplication of two functions in time domain is equal to convolution of their Fourier transform in frequency domain, which is also known as a generic version of a modulation property. This can be proved very easily by substituting above equation in Fourier inverse transform integration, and you can take it as a homework problem. In the next lecture, we are going to study a very important theorem, which is called sampling theorem. And in order to understand the sampling theorem, you need to understand all the three components which we have studied in our previous lecture, that is a Fourier series, Fourier transform, and properties of Fourier transform. And this is I would say, it is a stepping stone to start discrete time signal processing or digital signal processing. And hence, one has to understand sampling theorem in detail and its proof and the consequences of sampling in time domain in the analysis and designing of various discrete time system. I hope you must have enjoyed this lecture, and thank you for your patience and watching my show.